Alright, we continue with transformations and we're gonna move it a bit sideways and looking at introducing matrices. So a matrix is a rectangular array or a table of numbers of values. The numbers that you have inside the matrix are called entries, and those are examples of matrices of different sizes. Notice there's one as well with only one entry, and the bracket are square brackets on the outside. Now they will vary in size. The size is also called the dimension of the matrix, and you need to specify two values: the number of rows that you have here and the number of columns that you have over there. So the number of rows represents the horizontal lines, and the columns will represent the vertical lines. Okay, so the first one has 2 rows, 2 columns, so we define it by as a 2 by 2. The number of rows, and it's in the last sentence, the first number has to be the number of rows, and the second is the number of columns. So the order matters, especially for this. Let's say this one has 2 rows, 1 column. It's a 2 by 1. If you swap the order, it's the other way around. It will be 1 row, 2 columns. And you have the other examples, and the last one is a 1 by 1 with only one entry. We will focus on the 2 by 2 and the 2 by 1 matrices, as we'll link them to the previous part of chapter 7, which are the transformations and the mapping equations. Alright, so notice those two matrices, the 2 by 2, the entries are slightly different. So what it means is they are different matrices. For two matrices A and B to be equal, and we write it as A equal B, notice they bolded, but make sure you use uppercase or capital letters. The entities for the same row and the same column are identical. It means or they have the same number of entry at corresponding positions. So the first one, they must have the same dimension. That's what it means by the first dot point. Okay, let's look at some operation. There's 4 operations we're going to look at: addition and subtracting, kind of combined together. Multiplication by a scalar value or a real number, and then the last one is a little bit trickier, is the multiplication of 2 matrices. Alright, to add or subtract 2 matrices, they must have the same dimension, so the same number of rows and the same number of columns. So for example, here we have 2 by 2 and a 2 by 2, and what we do to add 2 matrices, what you do is you look at the corresponding entries, so the exact same position from the first and the second matrix, and you add the values. So adding the corresponding entries, for example, the first row, first column will be 1 plus 0, that gives you 1. First row, second column, 0 plus -3 will be -3. So here's a summary how to add also a 2 rows, 1 column, so 2 by 1 matrices. And what you end up is with the same matrix, one matrix of the same dimension. If you subtract, what you do is, again, the matrices must have the same dimension, the same number of rows and columns. And what you do now is for each corresponding entries, you do a difference from the left to the right. Okay, next one. Example. So here is adding two by two matrices, and a subtraction of 2 by 1. Probably pause the video, try to do that in your head. I think it's pretty straightforward. You don't have to write this down, and try to come up with the answer. Alright, let's continue. Here is the solution. So it has the answer by adding the corresponding entries, and here they subtract the corresponding entries. Okay, let's multiply by a real number. So it's what we call a multiplication of a matrix by a real number. When you multiply that, you start with a matrix of dimension m by n, means m rows, m columns. When you multiply by a real number or a scalar, the product, the answer is the same, a matrix of the same dimension, but the entries now have been multiplied by the real number or the scalar number. In this situation, they define it as k. So below is an example. You have that matrix 2 by 2, that gives you a 2 by 2. The entries will be each entry times 3. Okay. Now it's kind of also useful. So for example, when you add a matrix with itself, you can factorize it. So A plus matrix A is 2A, and what you do is multiply by 2 every entry. So you can do that for any size or any sum or addition of the same matrix. Kind of an information, the zero matrix is a matrix whichever dimension, but all the entries are equal to 0. For example, let me go back. See, when we did the difference here, we end up with a matrix with 0 as entries. It's a 0 matrix, which is a 2 by 1. Okay. So here we're combining adding and multiplication by a scalar. So we have 2a plus x equals b. We want to find x, so we can apply our order of operation by transposing 2a, which is what we have here. We substitute by the respective matrix. We multiply, we do the order of operation, so the multiplication by a scalar first, and then adding. We can combine that as in one operation, and here is the matrix answer. Okay, I'm in the way, but I think you get the idea. Okay. All right, the big one, multiplication of matrices. So you'll start with two matrices, A and B, and we're going to multiply A times B. Now the order matters, it's not commutative. So you start with a size, a dimension here and a dimension there. There's a lot of letters, but what's important here, and I think it's going to be outlined below, but here, that n here, from the first matrix, the number of columns has to match the number of rows of the second matrix. Okay, now here's the statement, how to do the multiplication. To find the entry in row I and column J of the product matrix, so the answer, by the way, the answer is a M by R matrix, so coming from matrix A, it's M rows, and matrix B gives you R columns, so the answer is a M by R. Let's go back to this. You single out the row I, so I corresponds to the row I here of the first matrix, and then the column J of the product, you look at the column J of the second matrix. You multiply the corresponding entries from that row and the column, and then you add the corresponding products. Bear with me, I know it's complicated, and I'll show you in an example in the next slide. We'll only do that with a 2 by 2 matrix, or kind of that size. As I mentioned before, the answer matrix, which is a dimension m by r, has the number of columns of, hang on, sorry, okay, so that note is saying that the number of columns of A has to match the number of rows of B, which I had already mentioned. Okay, let's look at the product. So we have a matrix A, matrix B. We want to do the product A times B. The answer, so this is a 2 by 2. That's a 2 by 2. That's a common, which is fine. But the answer matrix is going to be a 2 by 2 comings from the 2 and the 2 here. So it's a 2 by 2. Now we want to find the value of each entries. First entry is row 1, column 1. So row 1, column 1. What you do now is you look at row 1 of the A matrix, the matrix on the left, column 1 of the second matrix, and you, corresponding to the entries, so 1 and 5, 3 and 6, you multiply them together and then you do the sum. Okay, next one. It's row 1, column 2. So we're going to match row 1 from matrix A and column 2 from matrix B. We multiply the corresponding entries and we do the sum. Row 2, column 1. So row 2 and column 1 above. Multiply the respective entry. And the last one, it's row 2, column 2. And you multiply the corresponding entries. Then you evaluate all those using your order of operations, and here is the product matrix. Now let's look at a variation of that. Instead of doing A times B, let's look at B times A. So B times A here, I'm going to speed up a bit the process. So the idea again, row 1, column 1, row 1, column 1, and so on. So row 1, column 2, row 1, column 2, row 2, column 1, so row 2, column 1, and row 2 by column 2. You evaluate those and you get that matrix. Notice how that matrix is different from this one. As it is different, we can say that the products of AB and BA are usually not the same. They're not identical. Okay, let's do an example. So here is find AB. The first thing is make sure it's defined. To know if it's defined, so it's AB from the left to the right. So it's a 2 by 2 into 2 by 1. Therefore, AB is defined because that number of columns in matrix A is the same as the number of rows in matrix B. It needs to match as a rule, but the reason why is when you do, for example, you evaluate this, that's first row, first column, you do first row, first column, you can see the number of columns here and the number of rows have to match so you can do the multiplications. If they were different, it wouldn't work. So you must have those numbers identical. And then you get the answer by using your order of operation. Alright, so that's it with it's kind of an introduction to matrices, and we'll continue with applying that to transformation. And I'll see you later.